Hello, linear algebra student. This video is for chapter 4.5, dimension of a vector space. Now that we are done with different bases, one of the use of a basis is the number of elements in a basis actually tells us something special about the vector space, and we call it the dimension. Dimension is actually the um, the number of vectors that can happen in a basis. So for example, I have a vector space. It has one basis B of B1 to Bn. So this basis would be isomorphic to Rn. So our question would be, can I find another basis which has a different number of vectors, also independent and isomorphic to another Rm, like Rp or something? So this is the question that we are asking. Is dimension is number of vectors in a basis always fixed a number? Because they are isomorphic to something, right? So then we have two theorems to determine this, or one is any other vectors containing more than n vectors must be linearly dependent. So this is actually as a result of the fact that all vectors can be written as a combination of B1 to Bn. And if you have more than that, you can actually make a dependent sets. The second theorem is if there is every other basis, so you can make other basis of V must have exactly n vectors. So n is something that is specific about a vector space, which is the number of vector in any basis, and we call it dimension. So that this also implies that if you have a vector space and it has one basis of vector n, then every other linear independent set also have n vectors, and every other linear independent set in that vector space would span that vector space. Proof. So how do I know that it cannot be bigger than n? So just assume that there is one that is bigger than n, there's a set that's bigger than n. I can actually write, and they are linear independent, so I can write them all in terms of B. This would, of course, form a linear dependent set, right? Because n is greater than P, and all these are, in terms of B. So that means there's C1 to Cn such that if all these vectors are written in terms of B, that is equal to 0. So what we can do is you pick those C1 to CP and you combine it with U1 to UP, and this would also be equal to 0, having some non-zero CI. So it must be a dependent set and cannot be a basis. A basis has to be an independent set. So if you are more than P, it cannot be linearly independent. And then the other set would be if I have two sets, one has n vectors, the other has other than n vectors. So by theorem 9, the other one, B2, can only have at most n vectors. But if you switch them around, the other one can also be having at most the other vector. So they would have exactly n vectors. So this is the kind of the logic, both side logic. Another terms is finite dimensional versus infinite dimensional. Finite dimensional is if you can actually generate, the vector space can actually generate by basis that is finite from 0 to n. If it is the basis is 0, then there is one vector in the whole vector space, and it's the 0 vector space. The dimension is 0, so not 1. Okay, dimension is 0. There is this is a special case. It has one vector in the base. The vector is also the whole vector space, so it's dimension 0. For all the other one, like if you have the basis as one vector, so it would be dimension 1. If it cannot be generated or spanned by a finite set, then V is infinite dimensional. For example, polynomial of any degree, so n can be infinite, right? So you cannot have it spanned by a finite set, so that would be all polynomial of no limit as to the number of degree, it would be infinite dimensional. Example 1, what is the standard base for P2? That means polynomial of degree 2. So we know the standard base is 1, t, and t squared. Because any polynomial of degree 2 is written as a combination of C1 plus C2p plus C3t squared, right? So it's any P2 p of x would be like that. And so this is a standard base and it is isomorphic to R3. So is the dimension is 3. Okay, dimension of P2 is 3. So in general, dimension of Pn is n plus 1. Second example, I have two vector. H is the span of them. So that span means all linear combination of them. What is the dimension of H? Can we say it is a basis for the span? The only thing we need to check is that if they are linearly independent, right? Because I have only two vectors and they are not multiples of each other, so they must be independent, and they actually are part of the subspace, and all this other that means all the other vectors are linear combination of them, so it can be a basis for H. Hence, the dimension of H is 2. I have two vectors in the basis, so the dimension is 2. Example 3, I have described here I describe a subspace of R4. So it's a vector, every vector has 4 entries. And but it's not just A, B, C, D, but they have relationship with each other. So what is the dimension? Is it R4? Would this span R4? So to do that, we would actually write it in terms of, we would say this is x1, x2, x3, x4, or you can just say x, okay? And it's equal to A in terms of a matrix. So A, 1, 5, because there's no A, 0, 0, there's no A here, this 2, plus B, what's B? What's the multiple B? -3. That's how you add vectors together. You add the tops together. So it's -3. There's no B, 0. There's 1 and there's 0. Plus C of 6, 0, -2, 0. Right? Plus D being like the weights. And the vector that we can design is 0, no D, and then there's a 4D, there's a -1D, and this is a 5D. So this set of vector H is actually a linear combination of these 4 vectors. So let's find V equal to these 4 vectors, V1, V2, 1, 5, 0, 0. So they certainly would span H, because you can just do any linear combination of them to get H, right? Because that's how you define it. A, B, C, D are any variable, so any combination of them would actually generate this set H. But are they a basis? Because if I want to find dimension, I actually want to make sure that they are basis. So to do if it's a basis, we would we'll combine them into A, right? A x equal to 0. Solve this if they are linear dependent. If they are linear independent. We can also use IMT to see, because this is 4 by 4, so you can do a square matrix to see if it is reducible to a identity matrix. So either way is fine. Or for general, we'll just solve AX equal to 0. So if they are linear independent, they have the trivial solution, right? Only a trivial solution. So we would just do RLEF, right? So do the RLEF of 1, 5, 0, 0, 3, 0, 1, 0, 6, 0, -2, 0, 0, 4, -1, 5. Do RLEF using the decimal calculator. And I did it earlier. The beginning 1500 all this. So if I do A, I will see that it is not a identity matrix. Doesn't span out 4. Actually, it is span the one that is independence of this this Okay, let me write down 1 0 0 0 1 2 1 0 0 0 0 1 no 0 0 1 2 negative 2 0 0 and then 0 3 0 and then 1 0 and the last one is 0 0 0 0 0. So that means if I solve it equal to 0, um, x1 is equal to 0, x2 is actually equal to negative 2, x3. This is a free variable. Actually, and also this is also equal to 0. So they are not linear independent, but who x3 is the free variable that is a linear combination of the other, because x2 is equal to x3. So I can generate x3 by x2. So the linear independent sets are the one of the prefix position, right? Which is 1, the first 1500, the second 3010, um, and the last one 04 negative 14. The third one is dependent on x2. So this is a linear independent set. It also generate and also generate x3. So it is a basis because they are linear independent of each other. You can check by deleting this, and they would be all an identity or would have all prefix position in all columns. So they are a basis. So dimension of H is equal to 3 because I have 3 entry. So that's how you calculate dimension. And that shows that the way you describe it this way does not generate R4. How to find dimension of any subspace? So if they are not described in this way, or by spanning, right? Or describing how this. Now, is there what is the method? The method is to find a linear independent set that will actually span the subspace. So there is these two way that would describe a subspace. So for example, find a dimension of a subspace where the first and second entry are the same. So I'll write it out. I would say H is consists of R4. R4 would be like XY, like X1, X2, X3, X4. But what? The first and the second are the same. So I would say, well, let me use it AA. And because they're the same, then I have B and C, right? Where A, B, C are real number, right? So this would describe this set, but what is the subset that would generate it? I will write it just like what I write before. Write it in terms of x1, x2, x3, x4. In terms of some linear combination of vectors, like take A out, it'll be 1, 1, 0, 0, right? Take B out, take all those weights or the real number that they describe them, 0, 0, 1, 0. Take C out and it's 0, 0, 0, 1. So, and then I check that these three vectors are independent. So check by doing 1, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and then have them equal to 0, see if they have only the trivial solution. And I did that in B. So I put it in B and I do a row echelon of B. You can see that is x1 equal to 0, x2 equal to 0, so only the trivial solution. So AX equal to 0 have the trivial solution. This has only the trivial solution. Okay, so this is 1, 0, 0. Wow. So I just go too fast. So if I do RREF, this would be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and then 0, 0, 0, 0. I have a prefix position in every column, and they all equal to 0. So only trivial solution. So this sets B equal to that would be the basis, right? And so the dimension of X is equal to 3 because I have 3 sets. So 1, 1, 0, 0. 0, 0, 1, 0, and 0, 0, 0, 1.